Good afternoon, everyone. My name is Adil, and I was an applied ML intern with the AI engineering team over the last 8 months. Today, I will be going over the two projects that I've worked on throughout my internship at Vector. The first of which is on making a GAN architecture called FastGAN, even faster with JAX, and the other is a brief overview of work contributing to Vector's ongoing benchmarking effort. So here's a quick agenda slide. I'll first go over the FastGAN project, starting with what is JAX and why you should care about it, followed by a quick crash course on GANS, and finally introducing FastGAN and different results produced by it on our cluster. There will also be a very quick slide at the end going over the benchmarking project. So what is JAX? JAX is a Python linear algebra library released by Google that allows for very fast NumPy-like operations to be executed on an accelerator. Here are the three things that are making JAX gain rapid popularity amongst ML researchers. So the first one is that JAX provides native support for both forward and reverse mode automatic differentiation of arbitrary numerical functions via function transformations such as grad, JAC forward and JAC rev, which are forward and reverse mode Jacobians respectively. As you may already know, these are all very heavily used in ML optimization. Secondly, it allows for very easy vectorization using functions like vmap that converts a function that takes in a single data point into a function that takes in and operates on a batch of data. Lastly, one of the most important aspects of JAX is that it makes it so incredibly fast so that it offers just-in-time compilation using the XLA compiler, which is short for accelerated linear algebra. So what exactly is it that makes JAX so fast? For a very quick overview of how XLA works, it is helpful to look at what happens during the forward pass of a network when you do not use XLA. So let's say you have a function that computes the mean of x times y divided by z. Without XLA, when you run the forward pass, a graph is created. This graph launches 3 GPU kernels for multiplication, division, and the function computing the mean respectively. Each computation is done by each kernel and stored in memory before it is retrieved again by the other kernel. This storing and retrieving of intermediate values makes computation a lot slower. And now if you look at the XLA side, the process is the same up until where the graph is created. Here, XLA optimizes the graph, so a single GPU kernel is launched, which fuses all 3 operations into one kernel. Additionally, results are stored directly in GPU registers instead of memory, which allows for great speedups since there is no memory access overhead. So here's just a quick overview of how long it takes to train a few different popular CNN architectures on JAX versus PyTorch on the same hardware. So over here, it was trained on an RTX 3090. As you can see, JAX is often at least more than twice as fast compared to PyTorch. I'll also very quickly go over what GANs are for those of you who may be a bit unfamiliar with them. Essentially, you have 2 neural networks. One is the generator that takes in randomly sampled noise from a standard Gaussian distribution and outputs an image. And the other network is the discriminator, which takes in an image and predicts whether the image is real or fake. During training, the generator creates fake images, and you also feed in real images, which the discriminator can predict whether the input is real or fake. This signal is backpropagated through the generator, and all the weights are updated accordingly. So what is FastGAN then? FastGAN is a GAN architecture that allows for high fidelity images to be produced on a commercial GPU, like an RTX 2080 Ti, within a day with a very small data set size. I personally trained on data sets that are less than 1,000 images and sometimes even 100 images. So as for my main contribution, this model was implemented as the image use case model for the synthetic datasets bootcamp that took place last month. I had implemented a JAX implementation of FastGAN to allow for even faster training of an architecture that already has impressive results on other frameworks like PyTorch. One thing to note is that these speedups are primarily expected to be seen on TPUs, as JAX has been designed around TPU usage. Speeds for PyTorch versus JAX were identical on our cluster's GPUs. Vanilla GANs naturally are quite hard to train, and here are some problems with them. So deep generators work better, but are hard and slow to train. The reason behind this is that there is a weak gradient flow during backpropagation due to the extensive number of layers. Additionally, there is an increased computational complexity for both the forward and backward passes due to an increased number of parameters, which leads to a longer amount of time required for training. The solution to these problems in FastGAN is to use what's called a skip layer excitation module, as well as treating our discriminator as an autoencoder to learn better features from our real images. An autoencoder is essentially a network that learns to recreate its input for those of you who might be a bit unfamiliar. So here's a very quick overview of FastGAN's generator architecture. As you can see, these skip layer excitation modules are used throughout the network to allow for skip connections. I will not go into too much nitty-gritty details about the generator and discriminator networks in this presentation, as time wouldn't allow for it, but the main takeaway for the generator is the usage of the SLE modules. The input to the generator is Gaussian noise, and the output is a tuple of images that are then fed into the discriminator. So the skip layer excitation module, going a bit more into depth, it tries to fight these aforementioned problems and proposes an architecture that not only provides better gradient flow by taking inspiration from ResNets, but also does it at a reduced computation cost. It takes in two activation maps, but only one side is convolved down to a spatial dimension of 1 by 1, which is then used to do channel-wise multiplication. This results in us no longer needing to pay the price of expensive convolutions to match spatial dimensions. Another added benefit to this is that since we no longer need spatial dimensions to match, we are able to have these skips range over far greater spatial dimensions. For example, between 16 by 16 and 256 by 256. Here's also a very quick overview of the discriminator of the FastGAN architecture. Again, I won't go into too much detail here, but as you can see, there are two small decoders in green at the very end. And these essentially allow the model to recreate the input as to allow better, faster, and more informative feature learning of the dataset. The input to the discriminator is an image, and the output is a scoring vector. And quickly going over some results. I personally trained the FastGAN architecture for roughly 15 hours on a single T4v2 GPU on the cluster. And I trained it on a Pandas dataset as well as a Pokemon dataset. So here are some images of Pandas. This was, again, like roughly 15 hours of training time. And here's the results from the Pokemon dataset. These are all created from the same generator. Lastly, and very quickly, the benchmarking project was my first project at Vector, and I'll quickly go over some contributions I made without going into too much detail, as it still is a work in progress. I helped implement the cluster's most popular models on PyTorch's benchmarking suite, which essentially allows you to create arbitrary models and test forward and backward pass speeds on a given accelerator. I also helped collect and standardize results across different accelerators to help the computing committee make informed decisions. That'll be it for the internship demo. And if there are any questions, I'll be more than happy to take them. Otherwise, thank you for listening, and I hope you all have a great rest of your afternoon. Thank you.